That is 220 divided by 40. So 11 by 2, that is 5.5 ampere. Okay. And second is maximum instantaneous current in the circuit. Maximum instantaneous current, that is peak value of the current. Instantaneous current means it is fluctuating, it is variable. So maximum value of the fluctuating one, this means it's the peak one out. Okay, so peak value I naught is equal to IRMS into root. IRMS is I naught by root 2, so I naught will be IRMS into root. Okay, then it is time taken by the current to change from its maximum value to the RMS value. Means maximum value is this, and RMS value, let's say, is 5.5 ampere. It says what is the time, frequency is given to you. Okay, frequency is already present. PRMS is there, R is already given. Okay, R we have already used also in the first part. Now, time, current, and see how it is relating with the frequency. So if frequency is given, it says the time taken by the current to change from its maximum value to the root mean square speed. Means from this, whatever value of I naught, from I naught to IRMS, what is the time that is consumed? Say you already know the frequency. This means half cycle is being transmitted. Straight away for this question, see, time is equal to 1 by frequency. Using this, you can get the value. Okay.
Okay, ma'am.
Second is AC voltage applied to an inductor. This says, first one says a pure inductor of inductance. This is 25 millihenries. It is connected to a source of 220 volt. Find the inductive reactance. XL is missing, and the IRMS current in the circuit if the frequency is 50 hertz. Now it says XL is missing, frequency is given. See, linear frequencies basically, when you relate with omega, it is omega by 2 pi. So from here, omega can be written as 2 pi into the linear frequency. So 2 into 50 into pi, that is 100 pi radian per second. So that is the omega's value. L is already given as 25, then millihenries 10 to the power minus 3 Henry. Omega into L will give you XL. Okay. And for the IRMS current, voltage is there. From here, XL can be calculated. So IRMS will be, see, voltage by resistance. The resistance of the circuit, AC circuit having only inductor, is XL. So this, that way you will get the answer for the first part. Clear?
Yes, ma'am.
Okay, second says EMF is given. This whole equation is the equation of EMF. This is applied to a circuit containing an inductance 1 by pi. L is given. Write an equation for instantaneous current through the circuit. What will be the reading of an AC ammeter if connected in the circuit? Current is asked. But in the first part, it says equation of instantaneous current. See, you have omega from here. That is 100 pi. L is given as 1 by pi. XL can be calculated using omega into L. That is 100 pi into 1 by pi. So pi will be cancelled. That will be 100 ohm. XL will be this. Now XL is there, and it says equation for the instantaneous current. See, rest of it will not change, but you will have to calculate the peak value. Peak value will be peak value of EMF by XL. Now peak value of EMF is 220. So 220 by 100. That is 2.2 amperes. So 2.2, your equation of current will be 2.2 sine 100 pi t, like this. And a reading of an AC ammeter, if connected in the circuit. So see, if what will be the reading of an AC ammeter when connected, if connected in the circuit. Current you have got, okay, value of EMF you already have. right? So current,
Yes, ma'am.
whatever is the peak value of current is actually your answer. That is the reading of the ammeter
Mm.
if it is connected. It will give us the peak value only, right? So
Mm.
using the,
Yes,
no, it
ma'am.
will give us the RMS value. It is saying that it is connected to the circuit. So the circuit is supplied by the RMS value. So RMS we'll have to put. So what you do, you calculate ERMS first
Okay,
using
ma'am.
E naught by root 2,
Mm.
and then you calculate IRMS. Okay. Then you calculate
Okay,
IRMS
ma'am.
using ERMS by Excel. Clear?
Yes, ma'am.
All right. One more last. A capacitor of 1 microfarad is connected to AC source of this. Okay, same question. Okay, C is just there. Use omega. Same thing. XC is equal to 1 by omega C. 1 by omega is 100 pi. C is 10 to the power minus 6, okay, because it is farad. So same equation you can write using same thing, equation of instantaneous current, and for the reading, you calculate IRMS. This says that capacitance is given, inductance is given, resistance is given. They are connected in series. So C, L, and R, LCR, all the three are connected actually. It says what's the frequency. So 314 is the angular frequency divided by 2 pi. That will be 50. 50 hertz will be the frequency. This has to be calculated using um, frequencies omega by 2 pi. 3.1. That is 50 hertz. Okay. Reactance, omega is there, calculated using XL. This will be calculated using XL is equal to omega. Impedance of the circuit, big one, the whole complete formula of impedance you're going to use. Z is equal to under root this, that, and all. What is the current
Ma'am.
of the circuit? See, you have the peak value of voltage. Using this, calculate VRMS. Then divided by Z, that will give you IRMS. Yeah. ERMS will be 310 divided by root 2. E naught divided by root
Mm.
2. And current will be IRMS will be this ERMS which you will calculate from this side divided by the Z value which is calculated in the third part. Yeah.
Yes, ma'am.
And this should be remembered by you that this is pi by 2 which is 90. All right. So Basmi, quickly just copy down the things from here. And then we'll start with, see, before starting with total internal reflection, there's a topic glass slab that I didn't discuss with you. So I'll just tell you a little bit about the glass slab. Okay, because that is there in your syllabus. Then we'll move further. Okay,
Okay, ma'am.
please write it.
I'm done. I'm done.
All done?
No, ma'am, 1 second, I'm writing this. Yes, ma'am, done.
Okay. See, this is what I was referring to, bending of the light ray, and a little bit about the glass slab. We didn't discuss anything about the glass slab, and slab questions are there. So one thing before we begin, we need to know about the bending of the light rays. Okay, I hope I'm audible to you.
Yes, ma'am.
Okay. See, when I talk about the bending of the light rays, this means when the light travels from one medium to another medium. Let's say, now based on the refractive index, so let me mark it. Based on the refractive index, you have rarer medium and the denser medium. So when we talk about the rarer medium, basically rarer medium means whose optical density is less, refractive index is less.
Mm.
And denser means whose optical density will be more. Okay, refractive index will be more. So I told you refractive index tells you about the optical density of the material. So rarer will mean that it will have a lesser density. Okay, and denser will mean it will have a more density. And see, this density is not your mass by volume density that you have studied earlier. Okay, this is the optical
Mm.
density about the glasses, about the spherical glasses, which they are actually a part of. So whenever there's a light ray, let's say this is the normal reaction. Now, let's say a light ray is incident. Okay, this is where the light ray is incident. Or incident. Now see, this incident ray is there. So can you just tell me which angle is this?
Angle of incidence.
Angle of incidence, correct. This is angle of incidence. Now see, if let's say this is our rarer medium and this one is our denser medium. Now two different medium are present, right? Two different media are there. This is a rarer material, this is a denser material. So when you have a rarer medium and the light ray is going from the rarer to denser, it means two different medium are there, right? Two different media are present, which are separating. This is the interface. This is known as the interface. This is known as the interface. Okay. So in this interface,
Okay, ma'am.
this is the rarer, this is the denser. So light ray is traveling from rarer to denser. Now, if this medium change wasn't there, the light ray was supposed to move in this direction, right? Actually,
Yes,
its
ma'am.
path was supposed to be there. But when the light ray travels from the rarer to the denser medium, see, light ray tends to bend towards the normal. Now this means, look here. This means if I have this point, now this is away from the normal, right? This is the original path and you are going
Yes, ma'am.
away from the normal. This is what is meant by bending. Now towards the normal means like this. This was supposed to be the direction, but rather than going here, we are going towards our normal. Clear?
Yes, ma'am.
This direction, remember that this is your refracted ray. Refracted ray. and this will be the angle of refraction. Why? Because see, you always consider the normal. This green one basically represents the normal. Fine, is this clear?
Yes, ma'am.
So when light ray, I'll just mention a point. When the light ray travels from the rarer to denser medium, the rarer to the denser medium, it bends towards the normal. This you have to remember, okay? Towards
Okay, ma'am.
the normal. Okay, let's say one more case. This is the normal. Again, this is the interface. This will be the denser this time. Let's shift it. And this is the rarer. Okay, now this is your incident ray. This is the incident ray. So this will be your angle of incidence. Till here, everything is the same. This was supposed to go like this. This was supposed to be the movement of the rays. Now see, if this was supposed to be the light ray, this will be going towards the ray of light, right? And this will be going
Yes, ma'am.
away from the ray of light. Do you get it?
Yes, ma'am.
Towards and away means this is with respect to the actual position of the incident ray. Whatever was supposed to be the direction of the incident ray, this is based on that. So if we have this was there, this was supposed to be the light ray, like this would be going towards the normal. So we move like this. This is the kind of refraction. This is termed as that we are bending away from the normal. Clear? So towards the normal and
Yes,
away from
ma'am.
the normal's meaning is clear to you?
Yes, ma'am.
Okay. This is the refracted ray. This will be the angle of refraction. And I'll just mention a point as well that when light
Ma'am,
ray,
the angle from the normal to the refracted ray, right? Not till
sorry,
the.
yes, yeah, okay, total will be not with the. This is not even a ray. This is, I was just showing you the path. So you're right.
Okay, ma'am.
When the light ray travels from a denser means now optically denser, to a rarer medium, the refracted ray. This part was actually there in your 10th also. This thing, no?
Yes, ma'am.
Refracted ray bends away from the normal. Okay, clear?
Yes, ma'am.
So away and towards, you just have to remember which medium to which medium and what exactly is the meaning of away and towards. That's it. Fine?
Yes, ma'am.
All right. Just do one thing, copy it till here. Then one or two things I'll tell you in this before starting with total internal reflection. Apparent depth we have completed yesterday. Did you understand that?
Yes, ma'am.
Apparent depth, real depth.
Yes, ma'am.
Are you revising this chapter, Basmi?
Yes, ma'am.
So you've revised yesterday's portion.
Yes, ma'am.
So quickly explain me then what is apparent depth and what is real depth, their relationship. Take the help of the notes.
Um, Apparent depth is the depth from it's the depth from the surface till where we perceive the coin or the object to be, and the real depth is the actual place where the object is placed.
Correct.
And shift is the difference between apparent depth and the real depth.
Real depth. Okay.
Um,
And then
and then
they were
Snell's
related with
law
the
gives,
refractive index also. Tell me about that.
yes, ma'am. Sin I by sin R. Sin I is the angle with the real depth, and sin R is the angle made with the apparent depth. And it's equal to the refractive index in the for n2 by n1.
Okay. Okay, fine. Fine. Revise just the formula part a bit more and revise Snell's law properly. Okay?
Okay, ma'am.
Just revise Snell's law properly. And I want to complete the chapter before so that at least your nuclei, one of the chapters is at least done. Let us see how much we are able to do. I think we have 6 classes in this week left. If needed,
Mm.
can we have extra classes on some Sundays?
Yes, ma'am.
Not the next one. Let us just complete it. Let's see by the next Sunday how much we are able to complete. If we are on optical
Okay,
instruments,
ma'am.
then fine. Otherwise, then at the end of the September, we'll have extra classes at least so that your chapter is done and your syllabus is also completed. Right.
Okay, ma'am.
Just do one thing, Basmi. Copy this. I'll just offer a prayer and come. Okay. I'll just come in 2 minutes.
Okay,
Take
ma'am.
care.
Ma'am, can you scroll down? Ma'am, can you scroll down? Ma'am, I'm done.
Okay. See, this is a concept of multiple refractions, means different materials are connected. Air, then glass is there, then water is there, then again air is there. So when the light ray actually enters one medium, this is when refraction through multiple surfaces. Okay, this is refraction through multiple surfaces. Now, if a light ray passes through a number of parallel media, so parallel is important, okay? All of them are connected together. All the media are connected together. So see, this is not very important for you to remember, because see, if there's a gap, it means air is there. So that air should act as your medium. So means you should consider air, okay? Like
Ma'am.
this. And if the first and the last media are the same, means there is something present in between, like this. This is your air, this is your air. This can differ. You can have glass, you can have water, you can have oil, any other material, but this is the typical case that is given in the exam if it is given. Air is given like this, and means some material is there. Like instead of one single material, it just splits it into two parts. For one material, there's a concept of lateral shift that I'll tell you afterwards, but this is what happens. Okay, so air is there, glass is there, water, air, and all are there. So see, mu basically mu12 means n1, n1 means 1 with respect to 2, like this. Same thing, it's the same thing. So this is the first medium, this is the second, this is the third, and this is the first. Okay, air is your first, glass is the second, and water is the third. Got it? So this is back air. So this is your first medium. So what we do, see, if you apply Snell's law at every point, let's say if you apply Snell's law at A point, B point, and C point, so you'll get individual Snell's law. We did a question similar to this actually. Remember when two media was there, glass and water, and the ratio was asked. So what you do when you multiply all of them, whichever are the common will be cancelled. Okay. So like sine I1 is coming here, sine I1 is coming back. So these will be cancelled. Like this, sine R2, like this. So when you cancel all of them, means when you multiply, this will cancel this R2 will cancel this. What is basically happening? When see, this is your incident ray. This is the incident ray. Light ray has entered. This is the point. This is your normal. From the incident ray to the normal angle of incidence is I1. Then the next medium is glass. it refracted. So this becomes your first angle of refraction. Now, when you take the normal, again, this becomes this normal and this normal. They both become parallel. Here, I'll just mention all the normals are parallel. So if they are parallel by geometry, these become your alternate angles. So this becomes R1. Now this R1 is actually the angle of incidence for this glass water interface. Okay. So from here again it gets refracted and you get another refraction angle, that is R2. Now similarly this normal, let's say N1, N2 and N3, they all are exactly parallel to each other. So N3 is again parallel to N2. So the light ray gets refracted again, R2 and R2. These two become the alternate angles. So this angle of refraction now becomes the angle of incidence for this. And finally, it gets emerged out. Now remember one thing. This angle of incidence with which it has entered is exactly equal to this angle of emergence. This ray which comes out, this is known as the emergent ray. The final refracted ray is known as the emergent ray, and this angle is known as angle of emergence. Angle of emergence. And your angle of emergence and angle of incidence, they are the same. Angle of incidence is equal to angle of emergence. Fine? Angle of incidence is equal to angle of emergence. So these have to be the same. Then you can see when you multiply all of them, you get one. But the point is, if something is asked to you, then use this. Okay. And sometimes the questions come, prove that this is equal to 1, that the product of all the refractive indices is equal to 1. Then you have to show all the steps. If a numerical comes, it will be simply based on Snell's law at every point. So Snell's law is important, that I'll discuss in total internal reflection. This is clear?
Yes, ma'am.
Please write it. Then we'll do one formula.
Yes, ma'am. Ma'am, I'm done.
All right. Did you understand this, Basmi?
Yes, ma'am.
Now the lateral shift, let me tell you. See, glass slab. If we have a glass slab, this is just a specific case of the glass slab. The glass that is written is a glass slab. So the ray of light is entering from this medium. Okay, from air, the light ray is entering. Now this is the normal, and this becomes the angle of incidence. So this is the normal reaction. So again, now this is an interface. This is air glass interface, so refraction will occur because medium is different. So here the light ray bends, and since this is the normal, this becomes the angle of refraction. Now see, if you see, this is one line, this is another line. So if you notice over here, this total and this one, they are vertically opposite angles. Are they? Like this, like this. This is the angle of incidence, and this whole are are they vertically opposite angles?
Yes, ma'am.
Are you getting it?
Yes, ma'am. Yes, ma'am.
Okay. So they are vertically opposite angles. It means this complete is equal to angle I also, right? This complete is equal
Yes,
to
ma'am.
angle I also. Now from here, a part has been taken by R. So how much will be left? I minus R?
Yes, ma'am.
That's what has been written. That this much is this part. This is the I minus R. This is I, this is I minus R. Okay, so this was supposed to be the path of this incident ray if it wasn't getting refracted by the medium. This was the original path. This is known as the original path of the incident ray. This is the original path of the incident ray. Now, when this ray gets refracted, so not diffracted, diffraction is actually one more phenomena that we know. So this gets refracted. Now, this is another point. Now, this is the glass air interface. See, how do you determine this? Here, air is a rarer medium, glass is a denser medium. So look how the ray is bending towards the normal, rarer to denser towards the normal. And this is going from the denser to the rarer. Can you see this is bending away from the normal?
Yes,
This
ma'am.
was here. This was supposed to be the path of the incident ray. Okay, so this total is angle of incidence. Now see, when this ray gets diffracted, what happens is it is actually parallel to the original path of the incident ray. The final emergent, this is known as the emergent ray. Here also this is known as the emergent ray. So this emergent ray and original path of the incident ray, they are parallel to each other. Remember this. This is a conclusion from here. This is an experiment done. So here, emergent ray is parallel to the original path of the incident ray. Let's say the thickness of the glass slab is T is the thickness of the glass slab. Okay. So look here, when we say this parallel gapping that is coming between the rays, this parallel gap between the original path of incident ray and this emergent ray, this is known as the lateral shift. Got it? This is known as the lateral shift. So lateral shift, this is nothing but the symbol D in the formula, is equal to T sine I minus R by cos R. This is the formula of the lateral shift, where T is the thickness, I is angle of incidence, R is refraction, and this formula can be used as it is. Okay, so remember this formula. Okay, is this clear till here?
Yes, ma'am.
All right. Write it. If there's any doubt on this whole topic, let me know. Then I'll start with total internal reflection. Okay.
Okay, ma'am. I'm done, ma'am. Done, ma'am.
Okay, see now the process of total internal reflection. So this is a sort of refraction only, but ultimately there's a reflection in the final end. Okay, let's say this is our denser medium and this is our rarer medium. So light ray, the first condition for total internal reflection to occur is that light ray should travel from the denser to the rarer medium. Okay, from the denser to the rarer medium. This is one of the conditions. All right. So let's say
Yes, ma'am.
here this is the normal and the light ray travels from denser to the rarer medium. So if this was supposed to be the path of the light, it will bend away from the normal like this. So this is our incident ray, this is our refracted ray, this is angle of incidence, this is angle of refraction. Till here, am I clear?
Yes, ma'am.
Now, if I increase this angle of incidence more, let's say I am increasing this angle of incidence more. So what will happen? Let's say this is the angle of incidence this time. This whole, this complete is the angle of incidence. This is the incident ray. And we'll see that the refracted ray also gets bent more. Okay, this also gets bent. The angle of refraction also increases further. All right, let's say we have increased this once again, one more time. We have increased it. When you increase this is angle of incidence. Okay, here the refracted ray just grazes over the surface, means the angle of refraction is how much?
90.
90 degree, exactly. Angle of refraction is 90 degree. All right, now see, the angle of incidence for which the angle of refraction is 90 degree, this angle is known as the critical angle. This is known as the critical angle. The angle of incidence for which the angle of refraction in the rarer medium is 90. Angle of incidence in the denser medium, but the angle of refraction in the rarer medium is 90 degree. Now, if this is exceeded, means if the angle of incidence is more than the critical angle of incidence becomes more than the critical angle, the ray, now see, where will it exceed? It will come back to the denser surface only.
Yes, ma'am.
It's actually appears as if it is getting reflected. See, in reflection, this occurs. Incident ray strikes and it is reflected. So this is the refracted ray. This in this case, okay, this is the angle of incidence is more than the angle, critical angle. What happens? See, two conditions are there for total internal reflection to occur. One is that the light ray should travel from denser to rarer medium, then only this will occur. Second condition is that the angle of incidence should be greater than this critical angle. And what exactly is this critical angle? The angle of incidence in the denser medium for which the angle of refraction in the rarer medium is 90 degree. Okay. Let me discuss the
Yes, ma'am.
definition with you. See, the phenomena in which a ray of light traveling at an angle of incidence greater than the critical angle. It is written as IC also, it is written as capital C also. From denser to rarer medium is totally reflected back into the denser medium. This is called as total internal reflection, that is TIR. Now, what is the critical angle? The angle of incidence in the denser medium, for which the angle of refraction in the rarer medium is 90 degree. Angle of incidence is there in the denser, and R is equal to 90 degree, is called the critical angle of the denser medium, denoted by IC or C. I used IC because it helps you to remember, because C is the symbol for speed of light, but C is also there as the value. That's
Yes,
it.
ma'am.
This is the meaning of the total internal reflection, but it has a lot of application. I'll tell you the applications later. See here. First, let me tell you the Snell's law over here. If I apply Snell's law, what have we discussed? Same medium. Let me apply Snell's law at this critical angle point. So let's say here the refractive index is NR. So NR into sine R, NR into sine R. That's what I told you. Same angle, same refractive index is equal to, let's say this is ND, so it's ND into sine I. Clear? This is our Snell's law.
Yes, ma'am.
Now see, NR into sine 90 degree is equal to ND into sine I is what? Sine is IC. So sine 90 degrees, sine 90 is
1, 1. Sine
1.
90 is 1.
So NR by ND is the formula, which is 1 sine IC is basically 1 by NDR. This is also it is used. If I write see 1 by NDR means ND by NR. NR will go up. Just a way of representing it. NDR can be written as no ND by NR. So 1 by NDR.
Yes, ma'am.
Have you got it?
Yes, ma'am.
So this is all about total internal reflection. That's it. This is the formula. This is the theory, everything. We have to practice questions, and tough questions come from total internal reflection. Very tough questions come from this topic. It seems very easy. This is there in the theory part. No formula as such, just application of Snell's law, nothing. But questions are very tricky because applications are huge. I'll tell you this, we'll practice questions. So see, it's not difficult in the sense, if difficult in the sense when you don't practice. If you practice the questions of TR, then TIR is also not tough. It's just that you just have to understand the basic concept. Okay? Yes, you there?
Yes, ma'am. Okay, ma'am.
Okay. What happened? Your internet is not working, or you are inactive today?
No, ma'am. I think my microphone is slow. Whenever I speak, it goes slow.
Okay. All right. Please write.
Ma'am, can you scroll down? Done, ma'am.
All right. See, it says calculate critical angle for the glass air interface. Means glass air interfaces, I've drawn it opposite. This is air, this is glass. Okay, so light rays entering from the glass to the air. So denser to rarer. Now it says calculate critical angle. So like this will be the angle of incidence. This is the incident ray. And this is the reflected ray. And this is the angle of refraction. See, critical angle means when if this is condition says this is critical angle, you have to make this refracted ray graze over the surface. So this will be a refracted ray and directly angle of refraction becomes 90. Now you can apply the refractive index of glass. You can directly apply the Snell's law. You can directly apply the critical angles formula also. Both are absolutely right, whichever suits you. This sometimes this confuses me, NR, ND, and all. So you can apply Snell's law. If by anything you will get the same answer. Here it will be refractive index of glass into sine I is equal to This is sine IC actually, and the refractive index of air into sine 90 degree. Fine, so from here we can directly say critical angle is equal to 1 upon the refractive index when your medium is air, because the air's refractive index is 1, sine 90 is also 1, so that becomes 1 by n. So this is often used in the exams, means in the numericals one. Now for glass it is 1.5. Okay, that 1.33. For glass it is 1.33, 4 by 3. So that can be calculated. So sine IC is equal to 1 by 1.33. IC is equal to, this is an angle, so sine inverse 1 by 1.33. Clear?
Yes, ma'am.
Write it.
Okay, ma'am. Yeah, ma'am, done.
All right. Let's see one more question. Okay, this is a question from your NCRT only. Before the questions, I think we'll not be able to complete the questions. This is a lengthy and a very important question. Let me discuss the applications of TIR with you. Okay, few applications. Let me discuss one or two,
Okay,
because
ma'am.
this questions I need your complete attention. So on the next Friday only, I'll complete it. See, one is mirage formation. Have you heard of this mirage formation?
Yes,
What is
ma'am.
mirage? So basically, what happens? There are different layers of atmosphere. Okay, these are different layers of the atmosphere. So what happens? Different refractive indices are present in the different medium, right? So layers of the atmosphere are there, and these act as these act as relatively denser with each other. One is denser, one is rarer with respect to each other, though everything is air, but we are focusing on the layers of air. So what happens? The layers, they refract. Okay, they get refracted. And finally, a point comes when total internal reflection occurs. So when you have total internal reflection occurring, so what happens? Reflection means you will see the reflection of the object. So let's say there's an object, tree or anything. So you see an image on the road. So this occurs when very scorching sun heat is there, especially in desert areas. When deserted areas are there, so it appears as if water is present, and that's actually the reflection of the sky which is occurring due to total internal reflection. So it appears as if water is present but nothing is there. Or on very 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 warm hot roads, you are in Dubai, so
Yes,
the
ma'am.
weather of Dubai is also very humid, or it's
Ma'am, not inside, but if you go to the outers, yeah.
okay. All right. So, like this, because of different rays of atmosphere, because of different layers of atmosphere, the images are formed. So that is one important mirage formation that is often used in the literature terms also as a metaphor for many things. Then second is
Mm.
brilliance of diamonds. Brilliance of diamonds means, see, when you have a diamond with you, what happens is the light ray once enters. Let's say this is the light ray. The light ray enters, it gets totally internally reflected. Okay, then again here totally internally reflected, then here like this the light ray gets trapped. Okay, this. So now when you have diamonds, and if you just turn it a little bit, you are able to see its dazzling light turning. So that is because of the
Yes, ma'am.
light that has once enters, it's now trapped, and because of total internal reflection, it is getting trapped within itself. So here the refractive index of diamond is more. It has a very small critical angle that is almost 27 degree, and the light ray actually gets trapped here. Then this is a practical part. Just I'll tell you in the next class. Okay, let's continue this in the next class. All right.
Okay, ma'am.
Okay then. Oh, all right. Please do the assignments of ray optics now first. Forget EM waves and AC.
Yes, ma'am.
That I can start the discussion of this. Let's see how much we are able to complete in the next class. Lens are there. I hope lens are done. Spherical surfaces are there. Let's see then. Okay. All right. Okay then.
Okay, ma'am.
Bye. Thank you.